Hello everyone, this is a video lesson on equilibrium. What is equilibrium? So for us to say that an object or a system is in equilibrium, there are two possible conditions. So this time, let's first talk about the first condition of equilibrium. Now we can say that an object is in equilibrium when there is no net force acting on that object. So this means that there is no zero, or there is zero linear acceleration. So when we say net force or no net force, that means the summation of forces is equal to zero. An object can be either in static equilibrium or in dynamic equilibrium. When we say static equilibrium, it is not moving, which means it's at rest. Or if it's in dynamic equilibrium, it has a constant linear velocity, which means it is moving at a constant speed along a straight line or a straight path. So for us to easily analyze force systems, we can use free body diagrams. So free body diagrams are pictures that show the size and direction of all forces acting on an object. So it's a representation of a single body or a subsystem of bodies which are isolated from its surroundings and then showing all the forces acting on it. So this is an example of a free body diagram. So the free body diagram, literally it's free, meaning it's free from its surroundings. That's why we have to isolate this. We have to remove all other things from its surroundings so that we can just focus on this. And these are the steps to draw a free body diagram. So the first one is to pick one object to analyze. So for example, this is a table and there's a book on top of it. So let's say, for instance, we want to analyze the book, okay, on the top of the table. So draw a box to represent the object. So we will draw a box that represents the book, and then draw an arrow to represent each force acting on the object. So if we are considering the book here, so there are two forces acting on it. So the first one is the force of gravity, which is directed downwards. So this is weight, or the weight as we define it, it's the force applied by the earth on that certain object. So another force acting on it is the force applied by the table on the book. It should be something that moves or directed upwards to cancel this weight so that the book remains on the top of the table. And then make sure the arrow shows the direction and the relative size of the force. So since this object is at rest here, the book here is at rest on the top of the table, we assume that they are these two forces are equal in magnitude, but they are directed in opposite directions. So this is force. This is the normal force, okay, or N or Fn. So this is the free body diagram of the book on the top of this table. Now let's go back to the idea of equilibrium. Now let's focus on the first condition, where the net force or the summation of forces must be equal to zero. And let's say, for example, we apply one force here which is directed towards this direction, and the other one is, let's say, downwards, and the other one is going here. Now these forces A, B, and C, B has an x component which is directed towards the negative x-axis, while C has a negative y component, while A has both the x component and the y components. Okay, this is AY and then this is AX. Okay, as we can see here, AY is positive since it moves, or since it's directed upwards, and then AX is positive since it's directed towards the positive direction. Now we can say that this object is in equilibrium if the components or the x components of the force cancels. So which means E F x, which is equal to ax plus bx, which must be equal to 0. Okay, and summation of forces on the y component or y axis must be equal to 0 also. So that means ax plus cx, or sorry, that's y. This time it's y. Okay, this is ay plus cy. It must be equal to 0. Okay, note that the x component of c is 0, so that we don't have to include it here. And the y component of b is 0, so we don't have to include it in this equation. So these are the conditions for us to say that an object is in equilibrium. Now that we have already looked into the situations where the net force is equal to 0, now let's do these examples. So determine the magnitude of the forces acting on each of the 2 kilogram masses at rest below. So we have 3 situations here. So let's go to the first one. Now in this example, we have an object resting on a surface. So let's draw the free body diagram. So of course this object has a mass, therefore it has a weight which is directed downwards. So this is weight, and this is normal force which is directed upwards. So we assume that these two are equal since this object is resting. So if it's in equilibrium, it must satisfy these assumptions. So the summation of f of x is equal to 0 and summation of fy is equal to 0. Now since we don't have any x component here, so as you can see here we are only dealing with the y components, so we will just deal with this summation of fy is equal to 0. Now what are the forces here? So we have N, and then which is the normal force, minus the weight, which is equal to the mass times the acceleration due to gravity, and then we equate it to 0. So we can say that mg is equal to the normal force since they cancel. So therefore it's equal to the mass, which is 2 kilograms, times the acceleration due to gravity, which is 9.8 meters per second square. That would be equal to 19.6 newtons. Now in this case, we have 3 forces acting on the object. So if we will draw the free body diagram, okay, so this is the center. So there are 2 forces acting upwards. So this is the first force, which is T1, and then the other one here, it's also directed upwards. So this is T2, and then this one, the weight, which is twice as long, which since it's 20 newtons. So this is weight. Okay. Now again, we have to satisfy these conditions for us to say that it's in equilibrium. So summation of fx is equal to 0 and summation of fy is equal to 0. So again, we cannot see any x component here, so we disregard this one. We will just deal with summation of fy. So summation of fy should be equal to 0. Therefore, so let's deal with the tension forces first. So we have T1 plus T2. So they're both positive since they are directed upwards. And then minus the weight, which is equal to the mass times G, which is equal to 0. Okay, now we can say that T1 is equal to T2 since they are both perpendicular with this horizontal. Okay, so we can say that this is equal to T. So let's just use the T. So since let's go back to this equation. So we have T plus T, and then let's move mg on the other side. So that's equal to mg. So this is 2T. It's equal to the mass times gravity. So that's 2 times 9.8. It's equal to 19.6 newtons. Okay, so we have T is equal to 19 divided by 19.6 divided by 2. That's 9.8 meters, or sorry, it's newtons. So this is the value of T. Our next example is an object on an inclined plane which is angled 60 degrees with the horizontal. So first, let's draw the free body diagram. So it should look like this. So the first force that we can draw is the normal force. So this is the normal force. So it's the force applied by the inclined plane on the object. Of course, we also have the weight, which is downwards. And lastly, we have frictional force. So this is the weight. And since the tendency of this object is to move this way, okay, and we know that frictional force always acts opposite the direction of the motion or the possible motion. So frictional force should look like this. Okay, should be directed towards this direction. Now, for us to analyze this one, we can do a little trick on this. We can just rotate this image a bit so that the end should go upwards, and this here, okay, and then this is our frictional force, and this one, weight, should go like this direction. Okay, and this is our theta, which is 60 degrees. Okay, we just rotated the image. Now, okay, so we now have of course we have to follow the conditions. Summation of f x is equal to 0. Now let's identify all the components that are on the x-axis. So the first one is the frictional force, which is F. Okay, so since it's going towards the negative direction, so that's negative F. Okay, and then another one is the component of this weight, which is here. This, let's call this Fx. Okay, so that is plus Fx. So it's positive since it's going to the positive x direction. So that should be equal to 0. Now we can say that Fx is equal to F, and then F here. So f of x here, Fx here is the component of the weight, which is mg. So now this component here is also the same as this, and as we can see here, it's the opposite side of the angle 60. So that's mg sine 60. Since it's the opposite, we can use the sine since we can use, or as we discussed in our previous lesson, so if we deal with an opposite side and a hypotenuse, the hypotenuse here is the weight here, we can use sine. When we talk about the adjacent side and the hypotenuse, we can use cosine. So we use sine here since we this f of fx is the opposite side of the angle 60. Now, so because of that, we can get F, which is equal to 17.4 newtons. Okay, let's have some more examples. So for this one, the crate weighing 400 newtons is supported by 3 ropes concurrent at B, so meaning that all the forces meet at this point. Find the forces in ropes AB, so here, and BC, so here, given that P is equal to 460 newtons. So we can draw it like this. We have this box. So first we can draw the weight, which is downwards, and of course the force AB. So this is force AB. Again, this is weight, and this force AB is of course tension. So that's TAB. Next is tension BC, which is directed towards here. Okay, so this is 60 degrees. This is TBC. And lastly, we have TP, which is here. And of course, it's 460 newtons. We note that the angle between this horizontal and this force is 30 degrees. Now, in order for us to solve for TBC and TAB, we can use the first condition for equilibrium, which is summation of Fx is equal to 0. So the first component, the x component of TBC. Now, the x component of TBC is here. Okay, here. And then, of course, the y component is here. Now, if you will draw a triangle here, so the x component is the adjacent side of this angle 60. So we know that TOA. Now, since we're given with the hypotenuse, which is the TB or the TBC, and this side, the TBCX, is the adjacent side of the 60 degrees, we will use cosine. So that's negative TBC. Okay, it's negative because the x component is directed towards this direction, to the negative direction. Cosine of 60 degrees plus, this time we will get the x component of this, so which is 460. Again, we measure the angle with respect to the x-axis, and this side is again the adjacent side of 30 degrees, so we will use cosine 30 degrees. And then minus TAB here is this one. Okay, so it's directed towards the negative direction, that's why it's negative. Okay, now let's deal with the y component. The summation of Fy must be equal to 0. First is of course the weight, which is negative 400 newtons. Okay, times and then the second y component is the component of TBC. So since we use cosine for the x component, this time we will use sine. So since it's going up, we will use positive TBC sine 60 degrees. And then again, the third one is this y component of this TP or P. Now we have 460. So since it's going down, it's directed downwards, it's negative, so 460. Now since we use cosine to get the x component, we will use sine to get the y component. Now let's go to the second condition of equilibrium. Now for us to say that an object or a system is in equilibrium, there must be no net moment on that object, which means it must not be experiencing rotational acceleration, or the rotational acceleration should be zero. Now again, we have static and dynamic equilibrium. For an object that is not rotating, it's in static equilibrium, while when an object is rotating with a constant rotational speed, it's in dynamic equilibrium. Now here, I'll be showing you the two types of moments, so the positive moment and the negative moment. Now, a moment that is positive produces clockwise rotation, while a moment that is negative produces counterclockwise rotation. Now, for us to have an equilibrium, so the summation of the moments should be equal to 0. So meaning the positive moment should be equal to the negative moment in terms of the magnitude. Now to give you an example, for instance, we have weights here that are attached to 8-meter long levers at rest. Our task is to determine the unknown weights here, so this weight and this weight. Now since these levers are at rest, we can say that it's in equilibrium since there's no rotation. Now let's go to this problem. As you can see here, the forces F1 and F2 are directed downwards since they represent the weights of the first mass and the second mass. And F1 produces a counterclockwise rotation, while F2 produces a clockwise rotation. Now, because of that, this is negative while this is positive. So the values or the moments produced by F1 is negative, and the moment produced by F2 is positive. Now, as you can see here, the fulcrum or the force produced by the fulcrum or applied by the fulcrum is directed upwards, but it produces no moment since it is applied at this point, which the value of r here is 0. Now to solve for this F2, we have to use the second condition, which is the summation of moments is equal to 0. Now again, we have two moments here, the moment produced by F2 and the moment produced by F1. So moment 2 is it's positive since it's clockwise, and then we subtract the moment produced by F1, which is M1. Again, it's negative since it's counterclockwise, and that would be equal to 0. Therefore, we can say that M2 must be equal to M1. In our previous lesson, we calculate M from the force multiplied with the R times sine theta. So for M2, we have F2, then R2, and then sine of theta. In this case, we have 90 degrees, so therefore it's 90 degrees. So it's equal to F1 R1 sine 90 degrees. Okay, now since sine of 90 is 1, so therefore we can have this. So F2 times R, which is 4, so this R2 is 4, so 4 times 1, so that's equal to F1, which is 20 newtons, and then times 4. So we can cancel 4. Therefore, F2 is equal to 20 newtons. F1 is the same as F2, therefore it's equal to 20 newtons also. So similarly in this problem, we can again use the summation of m is equal to 0. So this is the second condition, and m2, so which is clockwise, so therefore it's positive, minus the negative, the m1 here, which is counterclockwise, that's why it's negative, so this is equal to 0. Again, we have m2 is equal to m1, so m1 here is f2r sine theta. So again, we have f2 times the distance from the r here, the value of r is 2, and then sine theta is 1, or sine 90 is 1, so this is equal to 20 times 3. Again, sine theta or sine 90 is 1. Okay, so this becomes F2 is equal to 30 newtons. Now from these equations, we can now get, okay, let's say we will use equation 2. So this is equation 1, this is equation 2. Okay, now from equation 2, okay, we can derive TBC. Okay, we can get TBC here since it's the only unknown here. We can say that TBC sine 60 degrees is equal to, okay, we have 400. By the way, we equate this to 0 first. So this should be equal to 0 equal to 0, so that we can satisfy this. And this is our equation number 1, and this is number 2. So 400 newtons. So we transpose this to the other side, and then okay, we have negative 400 newtons plus 460 sine 30 degrees. And then for us to isolate TBC here, so TBC is equal to 400 newtons plus 460 sine 30 degrees all over sine 60 degrees. TBC is equal to 727.46 newtons. So this is TBC. Now to get the other one, we can substitute this value here. Okay, so to equation 1, so substituting TBC to equation 1, since we have here negative TBC cosine 60 plus 460 cosine 30 minus TAB, so we will be able to solve for TAB after substituting. Okay, let's do that. So that's negative 727.46 newtons, and then cosine 60 minus TAB plus 460 cosine 30 degrees, it's equal to 0. Okay, now if we want to isolate this, so TAB should be equal to this one, so negative 727.46 newtons cosine 60 degrees plus 460 cosine 30 degrees. and that would be equal to 34.64 newtons. So this is TAB. The homogeneous 120 kilogram wooden beam is suspended from ropes A and B, and while a power wrench applies a 500 Newton meter clockwise couple to tighten a bolt at C here. Now determine the tensions in the ropes. So again, the best thing that we have to do is to draw the free body diagram first. So here's the homogeneous beam. So the first force is this one, the tension A, so which is directed upwards, while tension B is of course directed upwards also. While here we have a moment which is 500 Newton meter. Now since this is a homogeneous wooden beam, therefore we can assume that the mass is concentrated at the center of gravity, or so it's here at the middle here. So this is the weight of the object. So this TA, this TB. Now to solve this problem, we can use the first or the second condition, so which is the summation of m must be equal to 0. Okay, so let's identify all the moments here. So the first moment is this, which is 500 Newton meter. So since it's clockwise, it's positive. Now the second here is let's say weight here is equal to 100 kilogram times 9.8, so that's 1176 newtons. So the moment produced by this is counterclockwise. So since we assume that this system is rotating with respect to this bolt here, so that's negative 1176 newtons times the distance between this point of application or the center of mass and this bolt here is 3 meters. So since it's here, okay, the next is the moment produced by T or TB, so that's clockwise. So this is TB, and then the distance between this point of application and this is 2 meters, so that's multiplied with 2 meters. And lastly we have TA. Again, this will produce a clockwise rotation, so it's positive, so TA times 6 meters, and this will be equal to 0 as per this condition. Now, so we have two missing forces here, TB and TA, so we need another equation. So we can use the first condition, summation of forces is equal to 0. Now we only have here y components, so since weight is directed downwards and the two tensions are upwards, so we can say that summation of Fy is equal to 0. So what are the forces here? So first is TA, which is upward, so it's positive, plus TB, which is also positive, minus the weight, which is 1176 newtons, so this will be 0. Okay, now if we want to get TA, now let's isolate one. So TA, it's equal to negative TB, and then plus 1176 newtons. Now we have this equation for TA, so we can substitute this value or this equation to this one, okay, to the TA here. So 500 Newton meter minus 1176 newtons times 3 meters plus TB times 2 meters. Okay, so now plus, okay, so we have negative TB, so that's negative, let's make it negative TB times this 6 meters, and then plus 1176 newtons times 6 meters. Again, this is equal to 0. Okay, now we now have a 1 missing force here, which is TB, so we can combine that. So that's negative 4 meters times TB, and then so we can now isolate TB here. So that's 500 per Newton meter. So this can be positive now since we transferred it from the other side. So 500 Newton meter minus 3528 Newton meter, and then plus, okay, so this one 7056 newtons meter or Newton meter. Okay, so now TB is equal to, so that's 1007 newtons. So this is TB. Now to calculate for TA, so we will use this equation here, okay, and then we will substitute TB here. So negative 1007 newtons plus 1176 newtons, that is equal to 169 newtons. So this is TA and this is TB.